Mike. I hope everyone can hear me okay remotely. My name is Paul Elliott, and I'm from Embedded Security Solutions. We're a small consultancy company, and we actually come from ST Microelectronics. So in my former life, I was managing the security architecture group in the home entertainment division of ST. So hello to the ST people who are online today. Mike's asked me to come in and talk about hardware security. We've put together a presentation called Securing Smart Systems. So let's look at what a smart system is. Okay, so there are lots and lots of examples of smart systems today. We have a huge space in mobile consumer already. We have our smartphones and tablets. In home entertainment, we have pay TV systems. And increasingly in the home, we have automation. Increasingly referred to as smart home, and this is extending into buildings, and they'll be called now smart buildings. There are medical systems, point of sales, payment systems, and so on. The list goes on. All of these systems consist of software running on an appropriate hardware platform. Many, if not most, have communication functionality, typically supporting remote software updates, remote command and control, and reporting. And when they come with internet connectivity, as is increasingly the case, they are falling under the much abused banner, the Internet of Things. Okay. The threats to smart systems. Well, hackers will try to find an exploit allowing unrestricted access, if they can, to assets and or services. So, for example, financial, media, pay TV content being a prime example of that. They may even try repurposing devices, which is a particular problem if you're subsidizing your device within the market. A hacker will therefore attempt to gain control of the system. If the behavior of a smart meter can be altered, then there's an obvious financial gain to be had. You pay less for your electricity, for example. The ability to modify the software controlling a driverless car is very dangerous. A hacker could target individuals or groups and try to extort money from the manufacturer. So not very desirable at all. Of course, at its heart, the system is simply software running on a hardware platform, and the hardware and the software together need to be secured. What are the attacks? Modify the software running on the platform, so if you can simply reflash the device, then there's no underlying platform security, and clearly that's not a good thing. You may try to exploit design bugs, so unintended functionality, a mistake introduced by the designer. Or you might try and introduce a fault, for example, using a power supply glitch to put the system into an unknown state and exploit that. So they're all typical threats. What are the attack vectors? Well, the first thing to consider is access. Does an attacker have a local access to the system, or does the attacker only have remote access? So looking at local attacks, the first category of local attack is a logical attack. So a logical attack is exploiting the functionality as implemented in the device. So the functionality as implemented in the device may not be the functionality that was intended, and therefore an attacker may try to exploit bugs, in other words, design mistakes. If the attacker can modify the boot code by a simple reflash and a protection mechanism, then he has control of the system and it's game over. He may try to exploit debug or test functionality that hasn't been properly locked down. So these are all typical attack paths. If we look at local physical attacks, then these go beyond attacking the logical design itself. So, for example, injecting a fault into the system through the power supply using a laser, trying to find out what's happening in the system by looking at side channel leakage, so looking at the modulation of the power supply and EM emissions from the device, and more expensively physical reverse engineering. That's where you remove the die from the package, You look at it under a microscope, you try and delayer it, and you may even try and modify the device. And those require a lot of expertise, some very expensive equipment, and they're expensive attacks. So the return has to be worth the investment. The other category of attacks is remote attacks. So the attacker clearly doesn't have physical access to the device, and the attacks are over a network. And again, the attacker will try and exploit bugs. In the protocol, for example, he might try to forge messages or forge a software update to inject protocol faults, or to spy on messages and learn something about the system, which would help him attack it at a later stage. And the cost of a breach in such systems can be huge, particularly in payment systems. In order to secure a platform, we have to add some basic hardening. So locking down of debug and test functionality, and in terms of code running on the system, all code should be authenticated. So the boot code should be signed and checked, and any updates that are delivered over the air should also be signed. The communication interfaces must be protected, so use of signing and encryption of all messages, for example, using the secure socket layer. And the device itself, in order to perform these functions, requires to have encryption and authentication keys, and these keys must be protected. So public keys must be immutable. It must be possible for the attacker to change any public keys which are used for authentication, and secret keys must be immutable and, of course, not readable because they're secret. So all of this points to hardware infrastructure that's needed to secure a system, and this is commonly referred to as a hardware root of trust. So these are functions that are embedded in the silicon that you need to secure the system. Typically, we would embed cryptographic keys, so in model memory, for example, anti-fuse storage. We'd have a secure factory provisioning method, so that would be a way that you could manufacture in a non-trusted factory environment, perhaps in China or Korea, and you'd have a mechanism within the factory for delivering keys into the silicon in such a way that the manufacturer couldn't snoop the key delivery mechanism and see what the keys were. We embed cryptographic engines such as hash engines, SHA-256, and encryption engines. Key to many systems is a random number generator, so embedding a true random number generator, and there are various ways of doing this. Simple methods use jitter on ring oscillators, there are transition effect ring oscillator designs as well, which are more resistant to certain physical attacks. And many protocols rely on a random challenge response, so this is a key element in a secure system. A non-volatile version counter is very important, so an attacker cannot rewind software to a previous version or replay a message. And then in terms of running secure software in the platform, which is isolated, for example, from an Android stack, we need to have a secure memory space and secure interfaces which are mapped only into a secure processing space, and to provide a secure compute environment. And depending on the protection profile, for an advanced profile, we may require fault and side channel resistance as well. Okay, and again, these elements are collectively known as a hardware root of trust. They underpin the entire security of the platform, and you cannot have a secure platform without some or all of these functions. What does this mean for verification? Well, as you might expect, secure systems demand a very high level of verification. If you find a bug in a video decoder IP, for example, it may very well be that you can patch that bug and your video decoder works again. However, if you find a bug in the security IP, the same is not necessarily true. So if you have a hardware engine which is dealing with secret keys, and those keys are meant to be isolated from the application CPU, and there is a functional bug in the system which allows you to read those keys through the memory map in some way, then that is just not patchable. The system is broken and you need a hardware respin. Okay, so the cost of a security bug is much, much higher than the cost of a normal functional bug, because you can't necessarily patch that bug. So that's an important point. And whereas traditional verification has focused mostly on positive testing to ensure that the functionality you want is correct, security verification must also cover the negative testing aspects. So we must ensure that unintended functionality does not exist that could be exploited. So, for example, full code coverage is very important for VHDL and RTL, VHDL and variable designs as a minimum. In terms of interface testing, fuzz testing is a very common technique. So, where you're passing commands across the software or a register interface, in fact, commands and data. If there are unused opcodes, then you try fuzzing the interface with the unused opcodes and random data samples to see if you can put the system into an undefined state and maybe find an exploit that way. So that's a very popular technique. For very high assurance level systems, such as common criteria EAL7, it's mandatory to have full formal verification of the hardware. So, for example, security CPU may be verified against a formal instruction set architecture description, and there are various examples of this. If we look at the ARM7 architecture verification exercise was performed using a language called state machine insertion language, or SMAL for short, and you can find some material online which describes that. And this is the sort of thing that you have to do if you want to get the highest certification levels for common criteria and for EMV payment systems. Okay. So the next set of slides is taking a brief look at some of the more advanced attacks. So these are local attacks when you have physical access to the system. The first kind of attack, which is becoming quite popular these days with hackers, is side channel analysis. And this attack is based on the fact that the computations that are performed on the SOC device cause its power consumption to be modulated. And if the algorithm that you've implemented is performing computations which are data dependent, then you have a data dependent power modulation, and that leaks information. Okay, so by using side channel analysis techniques, you can actually extract secret keys from silicon if it's not designed properly. Okay, there are two main types of power analysis: simple power analysis, which will come to the next slide. I have a good example of that, and differential power analysis, which is a very advanced statistical technique which was discovered by Paul Kosher back in the 90s, and DEMA, which is the electromagnetic emission version of DPA. So these are all very powerful techniques to discover what's happening inside the chip and to extract secret information. The attacks are non-invasive, so relatively low cost. You just need a good digital sampling oscilloscope and the software tools to help you process the traces. And increasingly, the software tools are becoming available as open source. Okay, so you do need specialized knowledge. The budget is quite low, and more and more people are gaining expertise in these attacks. So they've become very, very important. And you'll find that if you want to make a payment card system, then it has to be resistant against DPA attacks, and that's mandatory. It's mandated by MasterCard and Visa, and you basically have to obtain a license from a company called CRI in order to do that. And they've pretty much covered all the countermeasures and patents. So it is more or less the only route. Specialist verification techniques are needed. So up until recently, let's say, people have built the silicon and then they perform physical tests on the silicon. They look at the power emission to try to attack it. But there is now some research going on using power simulations. So you come up with a design strategy, you run a power simulation, and you run the trace analysis tools on power simulation. There's some work going on there in the University of Bristol at the moment. This slide is a simple example. It's in fact simple power analysis, and this example as the RSA crypto system at its core is essentially very simple. It's based on modulo arithmetic, or clock arithmetic as it's sometimes called, and uses very big numbers. And encryption is performed by raising the message to the pad KE, where KE is the key, mod n. Okay. So how do we implement that in hardware or software? Well, the simplest way of implementing the modular exponentiation is to implement a series of squaring operations and multiplication operations. So the example we have here is a power trace, current versus time. And if you look at the peaks, you can actually see they have different widths. So the narrower peak is a squaring operation, and the wider peaks are squaring and multiplication operations. And the squaring operation represents an exponent bit of 0, and the squaring and multiplication operation represents an exponent bit of 1. So actually what you can do here, if you read the trace from left to right, you're reading the key bits. Okay, so you actually direct, with the naked eye, you're reading the key from this diagram. It's not a good situation. And this is one of the demonstrations that, if you go on the CRI training course, they'll show you, and they have a demonstration where a mobile phone is being used to perform an RSA computation, and they stand across the other side of the room with an antenna, and they pick up the radiation from the phone, process it, and out pops the key. And that's very good at scaring the credit card companies. And hence you find that that's mandated in the EMV specifications today. Okay. So that's quite a nice example because it's easy to understand. This is a picture of an EM probe station, courtesy of a company called RSA. Basically what we have here is an antenna, and we have a device on the circuit board, and it's on a jig, and you can move it in the X and Y planes. By doing that, you can build up a map, an EM map of the device while it's operating. So in this particular case, the operation is being performed repeatedly. And we scan the line, we see a red hotspot in the top right corner, and so we know that's where the crypto engine is. So the next step is to move the antenna over the crypto engine and perform more detailed differential power analysis operations to try and extract the key. Okay, so this is a much more powerful technique than just attaching a probe to the power supply line. Fault injection is becoming increasingly common. There are two main types of fault injection. So there's a power supply glitch. You can inject what's called an undersupply glitch. So you wait till something's happening in a particular clock cycle, and you tip the power supply by, say, 15–20%. And the effect of that is to change the flight time through combinational logic, and you might have a setup violation and cause a fault. Okay, so you can actually target particular operations. For example, doing lots of debug after this block. And then you have more directed fault injection techniques using lasers. That's a study of lasers technique because you have to remove some of the packaging, and then you can target a laser spot on a particular part of the circuit. That exploits the electric expression and the system off. And again, you figure out what to do by fault, for example. The countermeasures exploit redundancy. So basically, you have to add lots of extra logic for checking combat fault injection, so it can be quite costly. And we can verify the sort of used for how we can really have stuck up. You have to make sure your synthesis doesn't optimize all over the redundancy as well. So there's quite a bit of complication around adding the redundant logic, keeping it, and testing it. And then finally, physical reverse engineering is the most expensive attack, because you're talking about maybe using acid to remove layers from the chip, using scanning electron microscopes, and even using fib equipment to change the circuit that you're attacking. That's very expensive equipment and very specialized knowledge. So you only do that if you're retrieving an asset which can be used for a class attack. So the return must be worth the investment. Possible countermeasures include tamper detectors and active shielding. That's quite common in the smart card industry. Okay, and that's it. So in summary, good security is difficult. It's not free, but the cost of a breach can be very, very high. Can be much higher. Strong verification is a must, And advanced protection requires advanced countermeasures, such as signal masking and hiding algorithms, and new techniques to test those, built-in redundancy, tamper detection, and so on. So verification cannot be underestimated for secure systems. And that's it. Thank you.
So we're going to go for questions now. Any questions from Bristol? Excuse me.
Thank you, Paul. Can you just what are people doing with regard to protecting, securing DRAM?
DRAM. So we increasingly see people are implementing scrambling algorithms for content. Okay, so DRAM is particularly difficult because it's an extremely high-speed interface. You want high clock speed, low latency, right? And so traditionally people have implemented what they refer to as scrambling or obfuscation algorithms. So there's a trade-off there where you're basically lowering the cryptographic strength of the algorithm so as not to impact performance. And that has been acceptable for content up to HD. If we're looking at content systems, for UHD content, it's no longer acceptable. You need encryption strength of at least 80 bits. So we're having to look at highly pipelined block ciphers on DRAM interfaces. They can take up a huge amount of space. I think to get AES running at about 600 megahertz, you have to sub-pipeline the S boxes, and you're looking at something like 350k gates for each engine. So it's a huge impact to do that properly. And then if you're looking at things like TE, and you're not running everything in SRAM, which is probably the case because you don't want to put more than about 256k SRAM on a chip, probably. Then you're looking at putting TE assets in external DRAM. Then you have to have both encryption and authentication. So you have to add an authentication tag to the lines that are written from the cache to the DRAM. So it becomes really complicated. So I think to summarize the question, there are different approaches depending on the asset you're protecting in the DRAM. So from simple scrambling to higher strength HD content protection, and then up to TE level asset protection with authentication tags. And it does become very expensive.
Any more questions in Bristol? And there's another. No, I've got a question actually. Well, in terms, you mentioned formal verification. I think you mentioned the ARM7.
Yeah.
My understanding the ARM7 was it's formally verified quite a long time after it was delivered.
Probably.
And yeah. And I'm not aware of any real chips that have been completely formally verified. Is that really a requirement?
Yeah, well, what you'll find is that there is no smart card today which meets EAL7 level for common criteria.
Okay.
Yeah, you've got 5+ and possibly 6 now, I think. And 6 is semi-formal verification. So that is the highest acceptance level for common criteria, and nobody yet has met that. So it's a challenge to do it, I think, still.
And your definition of semi-formal is?
Well, it's a mixture of full formal techniques and ad hoc techniques, which are subject to a panel review. And so common criteria process is very documentation heavy, so you have to justify everything that you've done, and for a smart card program it can take about 2 years to get common criteria certification.
Okay, and one more question for me, following up on Hanan's point about memory. Are you able to I think one of the things you mentioned is the movement of memory, that certain places can't access other places. How would you go about verifying, for example, that a processor can't access certain parts of memory?
I think you just have to try. You have to try and access the memory basically. Obviously, you can't access the whole space, so you have to use random patterns over some of the memory space to do it. So it's kind of like a fuzz test, really, to make sure you can't access locations you shouldn't access.
Okay. Thank you very much. No more questions. Thank you. Next.